we will get going again. Okay. And this time, clock's right twice a day. I'm going to share my screen. Remember to share my screen. Okay, here we go. So agent-based models are a type of dynamic model. Dynamic models are this technique from system science we've just discussed, which depict in a simplified form a representation of the world and its evolution over time. All dynamic models share the characteristic of depicting at any one time the state of the system and characterizing in the model how the change in the state of the system depends on its current state. That's what makes them dynamical systems. Agent-based modeling is a very particular type of dynamic modeling that seeks to understand the behavior of complex systems through a certain lens, the lens of agent-agent and agent-environment interaction. Okay. System dynamics modeling uses other lenses, very powerful lenses, feedbacks and accumulation, for example. Discrete event simulation uses other lenses yet associated with resource constrained flow along workflow processes and queues, etc. Agent-based modeling focuses on agent-agent and agent-environment interactions. And it's an interesting thing that today's modern world of individual-based modeling brings together agent-based modeling, which has tended to come particularly from computer science and some social science background, on the one hand, with microsimulation modeling, which has tended to be an individual level tradition that hasn't traditionally emphasized as much agent-agent interaction. But certainly this emphasis on agent-agent and agent-environment interaction is quite central in the field as a whole. Agent-based models are upwardly facing models. And I say this in contrast to aggregate modeling traditions, which tend to sort of start with a high-level depiction and depict downwards. Agent-based, you have agents represented, and there's behavior of the system as a whole that's generated from that. There's no bottom there. Sometimes it's called bottom-up modeling. The fact is you can go down arbitrarily far, but it's upwards facing in the sense that we often have these populations of agents and they give rise to higher level behaviors. You saw it this morning with these agents whose weight was evolving and decisions about food choices and exercise were evolving. And it rippled up to those patterns we saw for the model as a whole, this relationship between weight and, distance to a convenience store or grocery store compared to convenience store, et cetera. Agent-based models vary strongly, and you will find traditions in agent-based models which emphasize stylized models that are very, very simple, more for theory building. Some of the work that Liz Bruch does or Ross Hammond falls very much into this sphere. Some of the work done earliest by Axelrod and Axtel, for example, likewise. But then you'll find other agent-based models which are quite descriptively rich and empirically grounded. And microsimulation tradition tends to emphasize such models. Now, we're going to be talking about some approaches for thinking through elements of agent-based models. And one of the sort of frameworks I'll be returning to here is this O'Party's framework for agent-based conceptualization, which thinks of agent-based models as composed as of having constituent parts involving outputs, specification of populations, parameters, actions, rules, time, and interventions, environments, and states. And I'm going to be talking about these components, as I described some of these models with you in the boot camp. But at a most basic level, an agent-based model involves one or more populations which are depicted at an individual level. And each of those populations involves agents which are characterized by parameters or attributes, fixed attributes. These could be discrete or continuous. It's important because we compare it against a stratified model, stratified aggregate model. For example, we're dealing with discrete distinctions there, age categories. Here we can have agents associated with continuous, continuous growth rates. So these are the things. Then there's state. That's the current situation of the agent in terms of something that evolves. So maybe a stereo that evolves, or their smoking status, or their preferences evolve, maybe, or their network connection perhaps evolve. The next two things are often confused, so I'm just going to use these, and this draws a lot in Ross Hammond's notion of the Partey framework. I'm going to distinguish actions and rules. And I should have a picture. Oh, no. So actions, so these would be the states, for example, these states here. So with respect to infection, a given person could be in a susceptible state or an exposed state, infected state, or recovered state. That's an example of a state. Their actions would be the sort of changes between states. So for example, this person could go from an exposed state, they're latently infected, to an infective state where they can infect others. They're infectious or infective. But there's rules that typically govern it. There's rules under which that action can take place. First of all, they have to be in the exposed state, but often there's other rules as well. Maybe this occurs at a certain rate, and any logic will depict that with that type of icon here. This illustrates sort of a situation where there's a certain hazard rate, a certain chance for a unit time that they will go. Maybe it's 1%, per day. They, for example, that this transition will be fired. Or maybe it's 1% per day. They'll go from a recovered state and their immunity will wane, so they're susceptible again. Other times the rules are governed by, they have to be, there's some external situation which occurs which pushes them along it, and we'll capture that with what's called a message transition. Or maybe it's a fixed timeout. After a certain amount of time infective, they will recover. Maybe it's 10 days. In which case they'll go across here after exactly 10 days. Those are rules. The actions here are the fact that they change. The rules are what governs those actions, under what conditions they will be triggered. Okay. And then they have a means of interaction with other agents. Commonly, those means of interaction are through networks or spatial environments. A model will also typically have a time horizon, sort of a horizon over which it's run, and a characteristic of that time horizon. Is it discrete, meaning it sort of advances and hops? These are sometimes called ticks or time steps. So maybe they're 1 day length, and it just simulates each successive day when Big Ben chimes, or Big Ben is still under repair. Or it could be continuous. It could be continuous time, as quickly or slowly as it continues. We'll talk about both of those in this boot camp. And then there's some initial state of the model. So let's talk about this. Let's make this more concrete. Okay, so we have a population. In the model, we will depict a population like this sort of population, that little icon up there. That depicts there is a population in this model of agents. Now, when we run the model, when we actually enact it, that population will hold a bunch of people. This is what's in the model. This is what, when we run the model, we see that population will have a bunch of people in it. So the model knows, okay, there's some population here with some number of people. And when I'm running the model at any one time, I'll have a certain number of particular agents in it. Agents will live in that population. Okay. And in general, in our model, we might have one agent type, say people, or it might be multiple agent types. Maybe we have people and service dogs designed to provide support for the veterans with PTSD who are represented in the population. Or maybe the other agent is a physician, for example. So we have physicians and or maybe we have a model in which we have deer and we have people who interact with the deer, and we have ticks or something like that. And we're looking at the spread of Lyme disease within the population, something along those lines. Now, each of these people in the population will have these parameters, will have these attributes. So maybe, for example, this person will have a certain sex. Well, maybe they'll have a certain income. Maybe they'll have a certain ethnicity, for example. And notice some of those are continuous and some are categorical, for example. Each of these people in this population will have those characteristics. In the model, we will say each person has an ethnicity, a sex, and an income. We'll say those are the characteristics of a person. And then when we run the model, they will enact that characteristic. Each one will have a particular value for each of those. Okay. So that's the distinction here between what you see when you build the model and when you run the model. So parameters here commonly represent, these attributes commonly represent fixed quantities. And it turns out that we will represent these with any logic construct called parameter. And this is going to define the assumptions about the agent or about the model as a whole. And so as we'll see. So when a baby is born, we communicate it through its parameters, or when we create a population, we say what the income distribution is, et cetera. We'll be seeing this. State would be things like this. So here's possible states for a person. And we talked about how there can be evolution in that state. Now, in an any-logic context, there are many different routes for evolution of a person. So we can time-out transitions, fixed rate transitions, a variable rate. These are different rules governing those actions by which a person's state will evolve here. So with state charts, we can have these different types of rules governing it. And there can be conditional routing, and we see here, for example, a person could be exposed to COVID, and with a certain probability, they'll get infected, otherwise they'll remain susceptible. So maybe they have a mask on and they're exposed and they don't get infected, in which case they'll sort of get exposed and they'll stay susceptible, is the idea here, compared to someone who gets infected and goes on to the latent infection state. So here we have these states and these rules for evolving the states. And we can have multiple state charts. Now, this is in contrast, in stark contrast to what we see with aggregate models, where we have a rather unruly and awkward multiplication of issues once we have to consider like multiple types of processes or health conditions. Here, we can parcel out at an agent level different types of concerns into different state charts. Okay, so we might have one state chart for someone's diabetes status, one state for their TB status, one state for their tobacco use status. This is not to say these are all solitudes, far from it. The use of tobacco might worsen someone's chance of developing for example, primary TB to be full on disease compared to latent TB when first infected. Or it may make it more likely that a person will reactivate from latent TB to undiagnosed active TB. But by parceling these out in different state charts, we get an economy of kind of specification that lets us specify how they interact in a crisp way, but avoids us having to deal with all possible combinations of states, which is really what we get in an aggregate model, where we have to deal with the combinatorics of it. Someone could be, in this state for this one, this state for this one, this state for that one, or this one and that one and this one. And we have to deal with all combinations. We don't have to worry about that here. Agent-based modeling supports in a enthusiastic way heterogeneity. In agent-based modeling, we can capture heterogeneity in terms of different types of health status, different health conditions or behavioral factors. We can also represent heterogeneity in terms of characteristics that are more fixed in a very easy way. If we want to add in a new characteristic here, suppose we wanted to add in someone's self-identified gender, for example, we could do this. Often that would be an aspect of stage, or maybe we want to add in someone's education level. If we wanted to view that as fixed, or their birth weight, we could simply add a characteristic to that person. It's quite easily done in the model. It doesn't require changes across the model. It's quite easily accomplished. By contrast, in an aggregate model, often we'd have to make changes that affect the entire model. They end up ramifying across the entire model. Okay, so just continuing on here. Okay, I should say something with stocks and flows. Some people here are coming more from a system dynamics background, so I just want to emphasize a point here. Commonly within an agent, we'll have multiple stocks and flows. I'm sorry, multiple state charts. We'll see this. We'll see this during the week quite a bit. We're going to have an agent who has state charts of multiple fleets. Each such state chart will typically represent a certain sphere of concern. Maybe it's for example, maybe it's a health concern. Maybe it's a aspect of their behavior, what have you. Great question. I'll come to that in just a moment, Anton. When we do this, it's important to recognize for each state chart, a person will be in one state, one of these simple states for each state chart. So if we had multiple state charts at the same time, maybe we have this one, for example, with TB, diabetes, and tobacco use. A person might be in the latent, a given person at a given time might be in latent TB use. They might be with chronic kidney disease, stage 2, and be a current smoker. Another person might be have undiagnosed active TB, be normal glycemic, and be a former smoker. So they're in exactly one state of each state chart at a given time. This just represents one aspect of their state. This is another aspect of their state. This is another aspect of their state. And for those for system dynamics background, just as the stock and flow model characterizes the possible states and the rules for evolving those states, so it is with a state chart like this. We'll be building up state charts, all of you, this afternoon, with some abandon, I might add. Now, often we want to represent features that are logically hierarchical. So, for example, we might be interested in representing social movement for deer here, for mule deer, which is different by season. So we have social movement, and we have summer movement, and movement during rut, movement in the winter, for example. Or we have general wandering movement, and then we have movement when they're going to food or going to water in sort of a directional way. They're seeking out a salt lick or what have you. So in these cases, we'll often have groupings. This is a set of infectious states, for example, subclinical versus clinical infectious states. And we'll see this, for example, in our COVID-19 modeling. So often with these state charts, we'll be depicting hierarchy in them that kind of group certain states. Okay, so I think I'm going to go light on this, but I do want to address Anton's question here. So Anton asked, how easily can ABMs incorporate population dynamics like new births? The answer is very readily, very easily. You can have open populations which have deaths or which have births, which have appearance of new members through immigration, or any of those processes. And in fact, I would view this as one of the areas where they can offer some quite unique benefits. For example, at the time of a birth, one can readily keep track of parentage or conditions under which the conception took place. It could, in principle, reason about relationships subsequently within the family because of that, et cetera. So births are represented as individual events. Okay. Now, this is and again, I'm tailoring some comments here for some of those from system dynamics background. George Richardson in the system dynamics area sometimes speaks about system dynamics modeling being undertaken at a certain distance from a problem. He speaks about system dynamics as having sort of a view that you're capturing general patterns over time without going into particular events. Agent-based modeling is a sphere where you're going into events. And particularly for continuous time agent-based models, you're undertaking them in an event-driven way, meaning a birth event happens, a death event happens, an infection event happens, a recovery event happens. You're down there in the events as they take place. In a system dynamics model, you have stocks and flows, and you just have a certain rate of transition from susceptibles to infectives or infectives to recovered. You're not getting into who exactly is recovering or how long they've been recovered for, who exactly is mixing. You're capturing the sort of flavor and the patterning of it. That's neither, I'm saying this in neither as an advantage or disadvantage. I'm just stating the difference in perspectives. So it aspires to step back a little bit and see these patterns, whereas agent-based modeling is very definedly at this level of individual actions and events, et cetera. And births are one of them. And births, so I don't know if anyone here is familiar with critical realism. Is that? Yeah, okay. So critical realist philosophy is one of these areas where health sciences has I think undertaken a real awakening to ideas that are very much aligned in spirit with dynamic modeling. The work of Pawson and Tilley I'd point to particularly as in realist evaluation, as laying out the threefold threefold considerations of context, mechanism, and outcome. Dynamic models in general are about mechanism. They're about why do we sort of the causal drivers for posited change in the world. They're about our theories of the world. What drives what? That's about mechanism. The mechanistic understanding of the world, the generative pathways, the causal pathways. I'm using different terms for it that maybe people recognize. But in critical realism, we also talk about beyond mechanism, context. And agent-based modeling is a tradition which really emphasizes context. And it does so through this mechanism of interaction of agents with each other. For example, and placement in networks. So one or more networks. So maybe someone will have a family network, and maybe someone will simultaneously have a collegial network, a social network online. Maybe someone will be in a needle sharing network, for example. These may be different networks. A person is in several at the same time, but they represent different aspects of context, right? The different aspects of relational context. Beyond this, we commonly have spatial embedding, okay? And in agent-based modeling, this too is strongly supported. So it may be irregular spatial embedding, where you're in an environment. It may be 3D spatial embedding. It may be sort of stylized, regular embedding. It may also be more geographic embedding, or geographically sort of inspired embedding. This for deer dropping prions, these misfolded proteins that cause chronic wasting disease. And in any of these contexts, we have situated agents. So again, harking back to critical realism, context and mechanism. This is capturing context, relational context in network, one or more networks, spatial context in some sort of space. But the final component is outcome. And so Pawson and Tilley have context, mechanism, outcome, and the realist evaluation framework. And outcomes here are also supported. We saw that this morning, where we saw outcomes. We happened to look at associations, but we could have looked at behavior over time. And indeed, behavior over time is a type of outcome that in agent-based modeling is of central interest. We see the evolution of an agent-based model in terms of changes in the number of people with certain characteristics in the population over time. Here we're depicting the number of agents over time who are in different states, clinical states or subclinical states of impact, or susceptible. That's very common. This is similar to what you might see in an aggregate model in the sense of depicting different compartments in an aggregate model, stocks in an aggregate model. Familiar probably for many of you. But here, each of these curves represents counting up individuals in the population. We're actually going through and saying, how many are in the clinical state? How many are in the subclinical state? It's kind of like we're going through each person in the population, counting them, sorting them into bins and saying, okay, we have this many of this, that many of that, that many of that. And really, that's a pretty good description of what happens in these models. Forget your mind thinking. This is about outcomes, and we can plot it out, but should remind you that the process we go through when we have an agent-based model are awfully reminiscent of what we do through with real-world data, or we might go through a survey of results and say, oh, this many said that, this many said that, this many said that. We're dealing with individual level data and aggregating upwards, just like we do often when we elicit survey, data responses from survey instruments. So, so this is outcomes that's over time. That's a frequent, theme in agent-based modeling. But we also have outcomes over space, right? And sometimes the patterning over space is striking. This actual model has a story behind it. Most models, this one has a pretty good poignant story. So we had for years been modeling chronic wasting disease, and chronic wasting disease and mule deer, particularly. We have strong researchers in that area here, and we built up system dynamics models in that area. Which are quite strong, and we were simulating the effects of environmental transmission and deer-to-deer transmission, etc. And it was insightful. It was great when we were simulating patterns over time. And then some students from one of my classes, from an undergrad, actually, who built this in my introductory modeling course. So they built up this model of chronic wasting disease as an agent-based model. Because some part of me feel it's a strong spatial component here. I'm really interested in what insights we might get from a spatial model. And they built it up and they ran it. And this is one of the first things I saw. It's like, oh my God. We were treating environmental layering of prions that's occurring. I mean, as you do in an aggregate model, we were assuming it's sort of the average level of prions over the environment. But what you see is they're really, really concentrated in certain areas. And they're concentrated in areas that are frequented, not surprisingly. That's why they're concentrated there. They're frequented by a lot of deer. And so, it leads to concentrations of prions in areas where, grass is good and deer can feed, or on the water shore where deer go for water, et cetera. And it can lead to greater risks of infection than you'd think otherwise if we're just spread out over the landscape in some sort of general way. So spatial patterning is important. Spatial patterning is sometimes important for understanding phenomena you see from the world. I used to run this model in the first section of this boot camp. And heck, if there's time, maybe we'll do it before we go to lunch. But you'll notice that there are these waves of infection that are going on here. And I thought they were kind of stylized for a while in an unrealistic way until I saw some pictures of the spread of rabies in some states in the northeastern US, particularly in Connecticut, Massachusetts, Rhode Island area, et cetera. And I saw patterns that also had these wave fronts that were not too dissimilar. And I said, okay, that's something I recognize, So it may be a bit stylized, but it captures an essential truth. This is a stylized model. This is a super simple model, as we'll see. But it's a model that, like a political cartoon or caricature, it brings out certain kind of stylized features of the situation, certain undeniable truths of the situation that are depicted. So within ABMs, we have interaction with the environment and agent to agents as a key components. Agent, a lot of it occurring with networks and sometimes with other mechanisms of sending each other messages for transactions or something. What's going to happen here, and you're going to see it within the next day or two, is agents are going to send messages to one another, again, across these networks. That's how they're going to speak to one another, is with this mechanism of a message. I'm going to be one agent. I'm going to say, I've exposed you to COVID. And, that will then have implications on your side. Then we have the spatial environments, which can be of different forms, but often involve agents encountering each other and interacting in transactions or otherwise engaging. And we can have embedded environments like this where agents may draw on resources in the environment or pollute the environment, contaminate the environment with pathogen or other forms like that. So these are different modes of agent environment, agent interaction. Okay. Often we have mobility patterns. We make use of GIS models, so geographic information systems, and the simulation often interacts with GIS data that relates to things like resource availability. So maybe GIS data is information on crime rates in different areas or pollution rates on different areas or Superfund sites in certain regions, and it exposes agents to this. And often there's a very healthy sort of interaction back and forth between what's in GIS and the agents. Okay, so we'll be talking about that some. Mobility is a common feature in many agent-based models with agents moving around this kind of semi-autonomous fashion. Okay, now agent-based models have an important feature that is absent in most aggregate system dynamics models. And again, because people's background, I want to speak to it. When agent-based models, we have randomness over time, or I'm going to use the term stochastics for this. Okay, there's uncertainty over time playing out. And you might ask why that is and why not in many aggregate system dynamics models. It has to do with that certain distance of which I spoke earlier, quoting George Richardson. In aggregate system dynamics models, we're taking a step back from particular events. We're asking about overall patterns. And often we abstract away from the details of what happens when we're dealing with sort of what are called mass action type rules often, and sort of general patterns of interaction that are occurring at large levels. Within agent-based modeling, we're dealing with events, we're dealing with particular circumstances and occurrences. And if we're dealing with individual behavior, if we're dealing with the occurrence of recovery or infection at an individual level, a pregnancy, successful births for deer, et cetera, we're dealing with uncertain factors. And as a result, it's natural in ABM that we capture things in a stochastic way. Whether someone goes to the convenience store today or the grocery store for a quick milk run might have some stochastics associated with it if the grocery store is a bit further away or what have you. And as a result, there's many implications. This has many implications for the models. First of all, when we run these models, if we run it one time, we'll see a certain result. Maybe we'll have over time a certain number of infections which occur within low socioeconomic groups. And at other times, at the same time, a different number that have occurred over the course of the model cumulatively in high SES. So a given run would give rise to this. A certain number that had been infected by the end of the simulation for low SES and a certain number for high SES, perhaps. And over time, we could plot those out, each of them, high SES, low SES. You notice the burden is much higher for low SES than high SES. These are socioeconomic statuses. So basically, poor people get infected a lot more. This is a given run of the model. It yields a particular sequence of events over time. The stochastics go a certain way by chance. Certain gatherings have outbreaks, others don't, what have you. And this is what you see as a result. At any one time, it's a certain number. But when you run the model again with the same assumptions, but different vagaries of stochastics, different realization, as we say, we see different outcomes. And if we run it again and again, we'll get patterns that emerge across that ensemble of runs. So if we run it again and again, maybe we'll see, cumulative high SES cases tend to be smaller than low SES. These are low SES. By the way, both of these have large numbers here, I think. You can only see the orange one. But I think both are very, very high here. But you'll notice high SES as a general rule tend to be lower. Any one run had a certain number of each. But if you run it again and again and again, you get a distribution for where high SES fall and a distribution for where low SES fall. A given run, 100% have fallen within this for the low SES number because it's just a single number. And same thing for high SES. If you run it again and again, you'll get a distribution. And you'll notice this distribution is higher than this one as a general pattern. And if you run it again, you'll find, there's some uncertainty about exactly how many have been infected by time 600, but it lies generally between 0 and 6 and 2000 for the low SES, and at that time between 0 and maybe 400 or something for the high SES. So just be aware, stochastics mean when we interpret results to avoid, we get different results with the same assumptions in the model. because of chance, happenstance, accident. What do we do? What do we do to avoid drawing conclusions that are from a thing that was just a fluke? We run it again and again and again. That makes sense? So rather than putting all our eggs in one run, one basket, we run it many times and we see the variability in results. And it's not just all over the place and just, goes just totally without order. No. Often there's a very clear order to it. It varies, but it varies within certain ranges. And often those ranges retain certain invariants, certain key properties, like high SCS burden is quite a bit lower than low SCS. Run again, pretty much for all of those runs, that's the same. And then a certain number of runs are almost, they're both zero. It's got the same. Yeah, Michael.
So is there like a threshold of variability where it would tell you that there's something wrong with the model?
Yeah, that's a good question. This, I will comment on that in this boot camp some. So one of the features that makes agent-based modeling more challenging is when you notice interesting behavior from the model or unexpected behavior from the model. That's the best way to put it. It's important to have humility and recognize there are two possibilities. One is this is really interesting emergent behavior, and this is fascinating, and I need to learn from this. The other is there's some chance this is a bug, and I want to make sure this is grounded, that this is actually coming from the model and not from some silly implementation mistake, some silly mistake I made trying to capture a model of a certain type, but I wrote times instead of plus or something like that. I did something. If we see model behavior that's like wildly entropic, it's just all over the place. You kind of get a sense that something is wrong and this needs investigation. And in general, I'd say when you see interesting patterns, what's really important is that you investigate them. And what's really important is you learn from them about what's driving them. You don't want to just step back and say, it's really interesting, I'll write it up and publish it. You want to say, okay, what is this telling? Because models are learning. Models are learning processes. They should speed us in our learning. We should go in and figure out why is it giving us this really interesting behavior? What is it telling you? What's the lesson to be learned here? And that's how agent-based modeling is used to really advance science, advance understanding. You develop a way of thinking like the model, what's driving it. These are all key factors. You don't want to just take the model as some black box that gives weird results and it's interesting. You want to go and say, like, so why does it do that? What's predominantly happening? And the beautiful thing is, compared to, we go through the same problem with the world, so there's no good bugs in the world. We're not sure what's causing patterns we see in the world, but with an agent-based model, we actually have the luxury of probing why we see these patterns by asking what-if questions with the model. So we can artfully choose what scenarios we run to figure out why are we seeing this. And often you push it to extreme scenarios. Say, let's turn on, let's set contract rate to 0. Let's have people never recover, or let's have people meet crazily frequently, or let's make it so people are wearing like 1,000 layers of masks or something like that. And you run it with these different scenarios and you see if the behavior retained. And you start to get a feel for, okay, what's driving? And it can lead to incredible insights if you pursue that carefully. And my students, will often have to pursue that for their projects. And part of kind of using a model effectively is learning why we're seeing these behaviors. And this is one of the reasons why building it up incrementally is so important. Adding things in bit by bit and learning how did that affect things? How did this affect things? How did that affect things? Really important for learning from the model. What's driving it? Because if you didn't see the pattern before, and now you add something in, and now you see a wildly different association, like those ones we saw early in the day, then you know, oh, okay, that must have been really important. Now I can go in and try to figure out why it was important, just looking at that change. This is really, really important. But this, figuring out, is it a mistake or is it something new? Or is it something that's substantive? That's much easier. All you've done is change one thing. Two things. You ran it before, you didn't see this weird phenomenon, now you do. Now you can really narrow it down because all you change is one or two. Becomes vastly easier to figure out why.
You might find that there's one maybe stochastic element that the model is really sensitive to.
Yes.
And then you might, does that tell you need to maybe then put data on that?
Precisely. It'll say like, this is worth putting a lot of effort on. So we had a model where exactly this occurred, and this turned out to be super, super important. And I got a grant just to fund collection of data on exactly that, and put $10,000 to $20,000 on just that data item because we really needed it for the model. We knew it was really sensitive to this, and I knew it was worth it. Okay. Any other questions related to this right now? Okay. So models are stochastic. Models can also be nested. We can have nesting like this. So for example, this probably doesn't mean much to you, but each of these squares is a city. Within each city is a social network of individual agents. The cities are linked together via transfer networks. So people can move from one city to the next. By the way, this model, example model says that many of these. Infection can circulate within a city, and then sometimes if an individual brings it to another city, it can move to another city. Another city. This is a model that captures nested context, hierarchies of context, person, and then city, and then region. And this is very readily accomplished within APMs. So we have these levels of context, persons, neighborhoods, schools, municipalities, countries. And in any logic, actually, in particular, this is really easy to capture. You can have, this sort of nesting of context. I mentioned stylized models. I'm not going to go into them in detail, but so I'm just going to finish here by saying something about ABMs, and then I think we're going to run a model together. I kind of like to run one before one, just to get things fired up a bit, get you thinking over lunch. And so when I come back and we interact with models, you'll have some beachhead already. Okay, so let's talk about some notable things. So they capture heterogeneity. When it comes to understanding health disparities, comes to understanding equity issues, when it comes to understanding transfer effects, when it comes to understanding diversity of behavior across in a population, ecosystems, heterogeneity is first and is a front and center. And if we want to design targeted interventions, target a certain high-risk groups, or want to engage in hotspotting and target vulnerable communities, we need to represent heterogeneity. And it turns out that's incredibly much easier within agent-based models compared to their aggregate analogs. It's easier to capture on continuous basis and on a discrete basis. By that, I mean continuous variables, discrete variables. We can represent networks, spatial context, multi-level nesting within these models in very elegant ways. We can capture situated decision-making. We'll have a talk about this later in the week about drawing on discrete choice theory together with models to represent situated decision-making of agents in a certain environment. Think an agent, certain preferences in a certain environment with certain options for them to choose. We can represent that very easily. And this sort of phenomenon, that dependentness are all around us. It's what traffic jams form in many environments. People, slow down on this curve of the highway because they can't see ahead or because the visibility is poor or what have you, and it ripples throughout the traffic jam. So situated decision making affects us, traffic behavior, personal protective behavior, mask use, etc. Vaccination decisions often based on experience within families, etc. We can capture longitudinal info. I haven't talked about this. When it was an agent-based model, you can accumulate history information on agents. I spoke about it in the context of telling stories, but this is profound. If you have an aggregate model, and again, I'm speaking to people who know about this. So here we have a SCIR model, or maybe we'll make an SCIRS model here. I'm putting this on the board for those who are attending remotely. I wish I could better capture that, but I put it on yonder board. Oh, that would be awesome, Larissa. Okay, now I'm in a pickle. Okay, I got it somehow. Okay. Yeah, that looks pretty good. So if you think about a model like this, very powerful for insights. Of course, it's nothing. I mean, the principles I'm talking about here go well beyond the disease model. It's just this is on my mind. What this gives you is a depiction over time of system state, the number of people here, number of people here, what have you. What it doesn't tell you is, is it the same people getting affected now that got infected, a year ago? Is it the same people? Is it different people? There's no individual stories here. It gives you a cross-sectional depiction of state at any one time. The number of people in the susceptible state, the number of people in the recovered state, etc. And that's powerful, but you're not able to really effectively ask questions about, how many people have gotten infected 5 or more times, and can we intervene on those people, those high-risk people? Could we intervene on the frequent flyers, for example, etc. We can't easily ask about individuals because individuals are not part of this story. We can't say those people at time of day, day 730 were infected. How many of them were the people that were infected at day 365? We can't ask that question because it's. I'm exaggerating a little bit, but the ability to ask those sort of questions is extraordinarily limited in a model that's aggregate. It gives a cross-sectional depiction over time. Agent-based modeling, by contrast, does allow us to capture this longitudinal information. And for those working with data in the real world in the health sphere, this is really important because often we do have data from the world that's longitudinal. We have data about, no fraction of people that are seen who have been infected before, or the number of times someone's been treated at an STI clinic, or we may have data on the time between COVID-19 diagnoses, in the Omicron era, or we may have data, about the average time from infection to representation or what have you. We have often data from the world that's longitudinal. And in fact, that data is often of greatest insight for its dynamic implications. But with an aggregate model, we're sort of ham-handed at being able to make use of it because we can't tell individual stories over time that are not well mixed in a mathematical sense. But here we can with agent-based models. We can have each individual accumulate their history, their story, their biography, And we can compare that with empirical data from the world and say, do these jibe? Are they consistent? Do these, is what I'm getting from the model have the ring of truth compared to what we see empirically? That's what we can do. And it's a very powerful type of insight. And it leverages that key data we just love in health sciences, which is longitudinal data at an individual level to provide those insights into how earlier experiences affect later outcomes, et cetera. Really key. It's important for calibration. It's important for model validation. It's important for interventions, designing interventions based on people of different histories. And if we can't reason about that in a compartmental model at an aggregate level, certain types of interventions can't be investigated. And I'd say if you're thinking about interventions, agent-based modeling is the right place to go if you're interested in many questions which involve implementation science, which involve issues of scale up, which involve issues of resources to implementations that are needed, how we design the intervention to be most effective and so on. These are much better probed with agent-based models, and a lot of targeted interventions are vastly easier to represent or feasible to represent with agent-based models. So we can often characterize more precisely sort of intervention rules and sort of guidelines that are really important for characterizing them effectively, particularly for targeted interventions. Visualization in agent-based models is very powerful. Interactive visualization is a part of many of our models. And if you can separate it from model logic, it's ideal. Have it not too tangled with model logic. Some of Wade's models excel in the visualization. And yet others we use R to do a lot of the visualization, of data after the fact, but some, in an interactive visual way. Yeah, well, I'll comment on the synthetic ground truth at another point. Okay, so those are all the comments I have right now. We're going to come back to this issue of sort of trade-offs and contrasts with aggregate models. I'm a vociferous believer in multi-approach modeling. And I believe that agent-based modeling is best conducted alongside and in concert with, and in many cases hybridized with other types of models. And we'll come back to that discussion at another time. This is our opening morning. Okay, so what I think we'll do is I'm going to stop this recording right now. I'm going to